Hi everyone. I just received some comments in the last few weeks, and I thought a few comments were very interesting since this is the placement season. I thought I should discuss one or two doubts from the comments. I do read the comments, but sometimes I don't get time, so I skip them. But this one was a very useful problem, so I thought I'll discuss this question, and I felt it will be useful for you guys who are sitting for placements. So the question is this: I had once discussed in, I think it's in the playlist op-amp circuits. It's in the lecture 3B. I was talking about the concept of virtual ground in op-amps. Okay, so I was taking different problems to explain what happens in an op-amp circuit when you introduce an impedance between the inverting and non-inverting terminals. Okay, so the idea of virtual ground is, if for an ideal op-amp, if ideal op-amp generally means the gain is infinity. If the gain is infinity, then we know V plus will be equal to V minus, and we called it this concept, if you in an inverting feedback in an inverting amplifier configuration, we call it as the virtual ground. Okay, it simply means your inverting and non-inverting node voltages will track each other. Okay, so this is a consequence of negative feedback, because for you to have a finite output voltage, if the gain is infinity, then the differential input has to be 0. Vd has to be 0, which directly implies this: V plus should be equal to V minus. So we were trying to slowly understand that, and in one of the problems, what I did was I introduced an inductor between the inverting and non-inverting terminals. And the question I asked in that, I think the problem was that instead of assuming this to be an ideal op-amp, assume this to be an op-amp with a finite gain, right? If the op-amp has a finite gain, then this is the voltage transfer characteristics of the op-amp, which means if your differential input to the op-amp is 0, the output has to be 0. That's a consequence of finite gain, right? If you have a finite gain, then there is a linear relationship between input and the differential, the output and the input differential voltage. So your V naught is simply A times Vd. If Vd is 0, then V naught has to be 0. For an ideal op-amp, if your gain is infinity, the characteristics would look something like this. I'm just quickly refreshing your memory. If your differential input to this op-amp is 0, the output can be anything. It doesn't have to be 0. Okay, so that's the difference. So I said, assuming that the op-amp's gain is finite, which means the graph should look like this. Here, assume the op-amp doesn't have any offsets and all that. So that means if you apply a 0 differential input, the output also has to be 0 volts. Okay, this follows from a voltage control voltage source model for the op-amp as well, right? The op-amp, it's a 3-terminal device, and we said that the op-amp's circuit model for the op-amp looks something like this. This is your 3-terminal model of the op-amp. If Vd is 0, then V naught is also equal to 0. Remember, the op-amp's output acts like an voltage source. So even though its output voltage is 0, it can sink and source any amount of current as desired. So this is something you'll have to keep in mind. And this is where I think I made a small mistake in the video, I think, which one of you pointed out. So what happens, again, just to stress this here, I was analyzing this problem assuming Vi is a DC input. Okay, Vi is a DC input. That needs to be mentioned here. Okay, now we'll come back to the problem. I just laid down all the basics that's necessary for this problem. So now it was given, I have connected an inductor between the inverting and the non-inverting terminals. The moment I do that, what happens in this circuit is that I am naturally forcing V plus equals to V minus, because inductor will act like a short circuit, which means I have forcibly applied input both at the inverting and the same input at the inverting and the non-inverting terminals, which means the differential input to this op-amp is 0. If the differential input to this op-amp is 0, the output voltage has to be equal to 0. So what happens if the output voltage is 0 here? So let me just draw this again. So what's happening here is that your inductor is forcing the inverting and non-inverting terminal voltages to be equal. Remember, they are not equal because of feedback. Usually in op-amp circuits, when you are analyzing them, the infinite gain of the op-amp in the presence of negative feedback forces V plus to be equal to V minus. But now I have directly short circuited the positive, and by putting an inductor at DC, it amounts to just short circuiting V plus and V minus. So I just short circuited these two node voltages. Therefore, V naught will always be 0. Okay, even if I keep changing the value of Vi, the absolute DC value of Vi. So let me show this Vi as a DC voltage source. Even if I change the DC voltage value of Vi, the output voltage will not change at all. So there is no feedback, negative feedback action at all in the circuit. Okay, this circuit, the output of this circuit is 0 volts. Now if the output of the circuit is 0 volts, what is the current drawn from the input? I think that's what I was interested in that problem. Now we know the ideal op-amp doesn't, generally op-amp is assumed to be of infinite impedance, so op-amp will not consume any current. So if this node voltage is at Vi, V plus is at Vi, V minus will also come to Vi because of the inductor. So therefore a current of Vi by R will flow through this resistor. Now since output is at 0 volts, this node voltage is at Vi, a current of Vi by R will flow through this resistor, the resistor in the feedback path. So now if you see, right, there are two paths for current, one through Vi by R and the other path through one through the resistor at the inverting terminal and one through the resistor in the feedback path. So the total current that flows through the inductor, the current here, if you apply KCL at this node, it will be split up as two currents, will be 2 Vi by R. So the current flowing from the input, which is same as the current flowing through the inductor, is 2 Vi by R. So I'll call IL as the current through the inductor. That will be equal to 2 Vi by R. Okay, I think I said something like V naught will be equal to Vi, which is not right. If you assume the op-amp's gain is finite, if A is finite, okay, then V naught has to be equal to 0. If V naught is 0, then a finite current will flow through the feedback resistor path. Okay, that current of course will flow through the op-amp's output. Since your op-amp's output is like a DC voltage source, it can support that current, okay, without any change in the output voltage. Okay, so that's something for you guys to keep in mind. And I can always, let's say an interviewer wants to complicate this problem, he might give you the op-amp as a finite output resistance R out. Okay, if you assume the op-amp as a finite output resistance R out, then you will have to write some KCLs and KVLs and figure it out. Okay, so the circuit will change slightly. What will happen is the circuit will look something like this. Let's assume this is R out here. This is the point you're tapping the output. So this node voltage will be 0, but your output node voltage need not be exactly equal to 0. So for that you will have to apply a potential divider. So this node voltage is at Vi. So let me just do that problem here, okay, because it's placement season, so I think any information is useful. So you'll have, I'm drawing the feedback resistor path here. This node voltage is forced to be equal to Vi by the inductor, and the output node voltage will be, the path to the output will look something like this. You'll have R out, and this node voltage is 0 because your op-amp's the VCVS output voltage, this is the point I'm talking about here. That node voltage, the internal node voltage of the op-amp will be at 0 volts. So now you can simply apply a potential divider here. So if I ask you to find what is the output voltage V out or V naught here, so this one is V naught. V naught will simply be R out upon R plus R out times Vi. Okay, so using that you can estimate how much current is being drawn by the feedback resistor path, and that in that case it will not be 2 Vi by R, it will be Vi by R through the inverting terminal resistor plus the current flowing through this resistor, which will be Vi by R plus R out. That will be your total current flowing through the inductor. Okay, so hope this problem is clear. In case you guys have any doubt on this problem, you can just pose your question, and I'll try to answer that. Okay, so it's an interesting question. I think it's good that you guys made some observation. See guys, remember I made this video 4 years ago, and usually I'm busy with some other work, so I may make some, generally, I mean, to the best of my ability, I try to not make errors, but most of the at least that was a recorded lecture, it's a live lecture, so I didn't prepare for it. It was delivered impromptu, so I might have made 1 or 2 mistakes here and there. Okay, so do point it out to me. I'll definitely get back. Okay, so that's this problem. Now the question is, what I'll pose here, I mean, we just analyzed this problem. If I just added an inductor and assume that the op-amp has a finite output impedance, I'm sorry, finite gain, then what will be the output voltage and the current drawn from the input voltage source. So the output voltage will be at 0 volts, and the current drawn at the input, assuming this, I mean, this node voltage will go to Vi, therefore the current drawn from the input will be 2 Vi by R. Okay, that's the same as current flowing through the inductor. If I assume op-amp's finite output resistance, I just showed you guys how to derive the current. The output voltage will not be at 0 volts anymore. The output voltage will come down to R out upon R plus R out times Vi. That will be your output voltage. Okay, understand here, or your op-amp's negative feedback action is no longer present. Okay, so that's the whole idea here. Now what happens if the gain of the op-amp is infinite? Okay, if I assume that the op-amp's gain is infinity, in that case, what will be, I mean, what changes will you see in this circuit? Now I'll just explain intuitively what happens. Remember, if your op-amp's gain is infinity, even if your differential input to the op-amp is 0, the output can be finite. Okay, output can exist, it can have some finite value. Okay, that's why it's a theoretical model. Ideal op-amps don't exist. Okay, so I just told you guys how to analyze if you have a finite gain. We just saw what happens. But an ideal op-amp is a hypothetical device, wherein I'm going to assume its gain to be infinity. So it doesn't matter whether you connect an inductor or not. It'll behave like a regular, because its gain is so high. Its gain is so high that even if you directly short circuit the inputs, you can treat as though the op-amp will behave as though it has some kind of negative feedback. Okay, so that's why it's a hypothetical circuit, and you will actually see that if your op-amp happens to be an ideal op-amp, which is not a theoretical possibility, but let's assume, which is not a practical possibility, but if you assume your op-amp to be an ideal op-amp, your output voltage will come close to 2 Vi. Okay, I'll do the exact mathematical analysis later, but what I'll do is I'll try to analyze a similar problem, but slightly a reduced version. I'll just remove the resistor on the inverting path. It's the same circuit. I just redrew the same circuit here, just that I've removed this resistor. I've just removed this resistor and drew it here. So it's just a voltage follower op-amp. It's an op-amp configured in voltage follower mode. I have just added an inductor between inverting and non-inverting terminals. Now what I'll do is I'll first analyze this op-amp as though I'm analyzing an ideal op-amp. Okay, so I'll assume the op-amp to be an ideal op-amp, which means your gain is infinity, and then we'll analyze this op-amp, and after that we'll assume a op-amp to have a finite gain, and then I'll show you guys using negative feedback analysis itself, you can show that the output voltage will come to 0. Okay, so let me come back to the analysis. So this circuit, to analyze this, what I'll do here is that I'll redraw the circuit slightly in a way that as though I can treat this circuit with a single input, as though it's like a circuit with two inputs, two identical inputs applied at two different points. Right? I've just took this inductor, I've redrawn the circuit this way. So this node voltage is at Vi, this node voltage is at Vi. Okay, it's the same circuit, I just redrew the circuit. That's it, there is nothing to confuse here. So we'll apply now the principle of superposition and try to find what will be the output node voltage. So first I'll assume this input is 0. See here, I've assumed both the inputs are independent but identical. Okay, that's the assumption I'm making. So therefore I'm assuming 1 to be 0 and try to find what is the gain. So this circuit reduces to an inverting amplifier, right? The gain of this inverting amplifier is minus of R by SL, the times Vi will be your V0. Let's call that VO1. In the second case, I'm going to assume input is present here and this input goes to 0 and your input is applied at the non-inverting terminal. Now the output here, let's call it V02, will be given by 1 plus Z2 by Z1. So 1 plus R by SL times Vi. Now your overall output V0 will be the superposition of the two voltages. So what will happen here? You will get 1 plus R upon SL times Vi minus R upon SL times Vi. So these two terms will cancel out. You are left with V0 equals Vi. Okay, so remember in this circuit I have assumed that the op-amp's gain is infinity. Because the op-amp's gain is infinite, even though the inductor is trying to short this node voltage to 0 volts, I have ignored its effect. I have assumed the loop gain is still finite, right? What is the loop gain? Loop gain is given by A is the op-amp's gain, multiplied by the feedback factor. Feedback factor here happens to be it's a RL circuit. You can derive the transfer function. I'll leave it to you. I'll write the final value. It will be a final transfer function, which is SL by R upon 1 plus SL by R. So this guy goes to 0 at DC, but if your A is so high, okay, if your A is so high that it's almost infinity, then I can assume that the op-amp gain can still be infinity. So let me take a very simple example. Since if you guys have already followed my lecture series on analog electronics, okay, I'll try to use an intuition to explain how this makes sense. I mean, I've assumed this to be, see, when I'm writing these equations, it automatically assumes that your loop gain is infinity. The loop gain is only if your loop gain is infinity, your V plus will be equal to V minus. Okay, only if your loop gain is infinite, you will have this condition being met. Otherwise, it will not work out. So now what I'll try to do, because if you have watched the first few lectures of analog electronics, I will try to use that intuition and explain why it works here. So let's assume the gain of the op-amp A is a function of frequency, and I can express it in this format, omega u by S. What is omega u? Omega u is the UGB of the op-amp. So in case you guys haven't followed those lectures, you can ignore it. But if you have already watched my lectures on analog electronics, you will be able to appreciate this discussion. So your A of S is given by omega u by S, right? So I told you guys that it can be approximated as a first order, as like an integrator. So DC gain happens to be infinity. After that, the gain starts falling off. For an ideal op-amp, I can assume a similar model of omega u by S with omega u tending to infinity. Okay, ideal op-amp gain is infinity for all frequencies, right? Which means if I say my UGB is infinity, see here, if I assume this gain model, it means the UGB is finite. So it is still not an ideal op-amp response, but this is a practical op-amp response. I am trying to say that if I have to use this mathematical model for an ideal op-amp, I have to use this approximation. What is that assumption? What is that assumption? A ideal. I am going to use this model, limit of omega u tending to infinity, A of S. I'll use this mathematical model, assume that it's a first order system, integrator model, which rolls off as a first order system with a finite UGB, but DC gain is infinity, but UGB is still finite. But if I let its UGB tend to infinity, then I have an ideal op-amp gain response. This is a theoretical model for the ideal op-amp. So that's what I'll do here. I'll substitute the expression for an ideal op-amp in this response. So what is your loop gain? Your loop gain is A of S is the amplifier's gain multiplied by the feedback factor, beta here. Feedback factor is a simple RL network, R and L, and that you can derive it to be SL by R by 1 plus SL by R. Now if I assume A of S to be omega u by S, what do you get here? You get omega u by s times SL by R. S and S cancels out, and you're left with omega u into L by R divided by 1 plus SL by R. Okay, so this is your loop gain of S. Now since I assume the op-amp to be ideal, omega u tends to infinity. If omega u tends to infinity, this entire term will tend to infinity, which means your loop gain is still infinity. So that's why I meant, if I use a hypothetical model where I'm assuming the gain of this op-amp to be infinite, if you assume this op-amp to be an ideal op-amp, I can theoretically assume the loop gain is still infinity. Okay, and that I'm not wrong in making that assumption. And I've shown you guys why that assumption is not wrong by using a simple mathematical model for the op-amp or the op-amp's gain response. Okay, I just assume the ideal op-amp's response. You take a practical op-amp's response, frequency response, and let its UGB tend to infinity. Then you get ideal op-amp's response. And if you assume this as your ideal op-amp's frequency response, where omega u by s and omega u tends to infinity, you can show that the loop gain itself will tend to infinity. Okay, so therefore, because the loop gain tends to infinity, I am just directly using, I've written all these results, when I was analyzing this, even though there was an inductor present, I just wrote 1 plus R by SL. I can't write this expression because your inductor will ensure that the DC feedback factor is 0. Your beta Fs is 0 or DC, right? S equal to 0 means DC. If beta Fs is 0, how can I write this expression? I'm telling you guys that if your op-amp is ideal, you can still do that. And I just gave you guys a mathematical justification for that. Okay, so that's the understanding here. So therefore, even if you take this circuit, you can do the same analysis for this circuit as well. This circuit is little bit more complicated. The feedback factor, you will have to take into account this resistor and all that. But I think at DC, it reduces to a similar version, a similar circuit. So I've just taken this circuit and I just told you guys that if you assume this op-amp to be an ideal op-amp, then your V0 will come to equal to Vi. That's what we showed here. You add the two voltages, V0 becomes equal to Vi. So this circuit here, V0 will become equal to Vi. This node voltage will be at Vi because inductor will short it, or you can see it that way. This node will be at Vi and there is no path there will be no current flowing through the resistor. In fact, this circuit will behave exactly the same way as this circuit, as though there is no inductor at all. The presence of inductor really doesn't matter to me. That's what this is telling me. Okay, it will behave the same way as this circuit. It's a voltage follower. V0 will come to Vi. This node will also be at Vi. Current flowing through the resistor will also be 0. Okay, this is the same as a voltage follower with an ideal op-amp. Now I'll assume the op-amp gain to be finite, and we'll apply the same principle. We'll apply the same analysis procedure, wherein I'll assume this. We'll assume we have applied two independent but identical inputs at two different points. Okay, I've taken the same circuit, which is what we started with this circuit here. I'm sorry. So we started with this circuit here. Okay, this circuit here, and then I'm applying principle of superposition. So let me just redraw that circuit here. So this is I'm just redrawing the superposed version. So L, R and Pi. So first I'll assume this input to be 0. So this node voltage is at ground. Now I'm assuming the op-amp's gain is finite, meaning your op-amp is described by a VCVS voltage model with a finite gain. If the gain of the op-amp is finite, inductor will short circuit this node voltage will come to Vi. If this node voltage comes to Vi, what happens to the output of the op-amp? Your output of the op-amp will come to V0 equals minus of A times Vi. Right? A is the op-amp's open loop gain multiplied by Vi. right? The differential input to the op-amp is minus Vi. So therefore your output of the op-amp will simply be minus of A times Vi. Now I'm applying the input at the non-inverting terminal, and I'll short circuit this input and try to find out what is the output node voltage. The moment I short circuit this node, automatically the inverting node voltage will also come to 0, because inductor, it will just short circuit this node at DC. Okay, it's like a wire with 0 resistance. You can just short this node. Now you are left with Vi being applied at the non-inverting terminal, and V minus is at 0 volts. So the differential input Vd is Vi. So the output voltage will now come to V0 equals A times Vi. Okay. So in the first case, in the second case, you get plus AVI. In the first case, you get minus AVI. Apply principle of superposition, you will get 0 volts at this point. The inverting terminal will be at plus Vi volts. Okay, so in the second case, the inverting terminal voltage is at 0. The first case it is at plus Vi. So you add the two voltages, you will get plus Vi. So this will be at plus Vi. So the current flowing through the resistor, because output is at 0, will be Vi by R. And that's the same current that's flowing through the inductor, and that is also the current that is being drawn from the input voltage source. So the current flowing through the input, II, is simply Vi by R. Okay, I mean, you can see that even in principle of, when you apply the principle of superposition, you can see in the first case the current flowing will be, because you applied Vi here, it's minus AVI. You will have a negative current flowing in this direction. Okay, sorry, this is negative, so therefore current will be flowing in this direction. You can calculate that current. It will be 1 plus A times Vi by R. That's the current that flows through the resistor. In the second case, the current flowing through the resistor will be in the opposite direction. The magnitude, the value of the current will be A times Vi by R. So you add the two currents, right? The current's polarities are different. You will end up getting Vi by R. Okay, Vi by R flowing in this direction. That's it. So that's what's happening here. I just gave you guys an intuitive analysis using principle of superposition to explain what exactly is happening in the circuit. And it's a good catch. I think one of you wrote to me saying that I made a mistake saying that in the previous lecture that there will be no current flowing through the resistor, which is wrong. No, I made a mistake there. That's a good catch. So hence this video. Okay, thank you.